In this project, a study of polar code for video transmission over wireless medium was done, using software-defined radio platform. What happens when your Wi-Fi or cellular signal strength is low? Would you be able to stream high-quality video without buffering? What is forward error correction? It is a technique to identify the corrupted information and correct them to some extent. There are lots of error correction mechanisms, and bit error rate is a way to measure its performance.
Forward error correction is being used in cellular communication technologies such as 3G, 4G and the upcoming 5G standard. Also, communication technologies used to control deep space missions use forward error correction techniques. Polar codes are a family of error-correcting mechanisms, proposed by Eriken in 2009. This code has been mathematically proven to be better than other error correction techniques, such as LDPC, and turbo codes. Polar code implementation is less complex compared to other systematic codes. In this course project, I have implemented polar code encoder and decoder in a GNU radio platform. Using this, a study was made for different digital modulation schemes for transmission of image, and video streaming was done. The left image shows the polar code encoder and decoder blocks, which were implemented on the GNU Radio Companion platform. On the right image, two USRPs are shown. One was used as a transmitter and one was used as a receiver. Both were connected to the same computer system via Ethernet cable. As we can see from the graph, polar code decoder with CRC is not having a higher block error rate. Therefore, SCL decoder without CRC was implemented in the GNU radio platform. The graph was obtained by running the polar code encoder and decoder code in MATLAB for different list sizes. The block diagram shows that CRC check as proposed in Alexander Vardy's paper is not used in the SCL decoder architecture. The block diagram shows the overall architecture of the study being made. Information sent could be a random data, text, image or video. We compare the word error rate for different modulation schemes. In this study, we found that OFDM with 16 cam was slightly better in word error rate performance because higher block sizes can be carried with 16 cam with less delay. The graph also indicates that the study was made for different levels of noise. Image 1 indicates the transmitted image, and the image 2 indicates the received image after polar code decoder. The received image lost 20% of information. By using the polar code we recovered some amount of information, whereas the image file would be corrupted if there is no polar code block. The image transfer was done at 80 decibels of noise level. Video streaming was done on different video samples using GStreamer tool. Bit error rate calculation framework used for earlier performance measurement didn't work with the video streaming application. Hence, packet loss during video streaming is used to measure the performance. The table indicates that packet loss with polar code blocks is less compared to when no error correction is used. On the right, you can see that the video streaming is being done. We have a higher block length and higher list size to improve the error correction. Due to this, the decoding latency is high and video streaming is choppy in nature. To achieve higher quality video streaming, the receiver blocks needs to be implemented in the hardware. When the receiver blocks are implemented in the hardware, we can explore higher parallelism of the SCL decoder. Also, BPSK demodulation scheme was implemented in the FPGA, which had a significantly lesser area compared to OFDM with 16 cam demodulation scheme. SCL decoder resource usage and their throughput is shown in the table. Thus, study of polar code for video streaming in worse wireless environments was done. However, the idea can be improved in these possible directions. There are many types of decoding schemes proposed till now by various researchers. Some have higher error correction performance, some have lower latency. Based on the application and its latency needs, we can choose the decoding scheme to be used. Also, resource usage of OFDM needs to be reduced when implemented in the hardware.